Thank you very much. It's a privilege to be here to speak on this topic, optimizing on-target canopy deposition in citrus, considerations for minimizing spray drift potential. And this is a very important topic, at least to me, and I know to many of you, because we all know what the implications of having drift, pesticide drift from an application site to nearby communities, or generally having a spray pesticide drift from an application site to off-target or off-site locations where it is not necessarily intended to get there. And we know the implications in terms of the environment, and also the potential for human health implications. So I would want to start off by taking us to the field. And let's look at it's an air blast spray application in a typical citrus orchard. And as you can see here, I can't point. Okay, so you can see that in this particular application, we have a sprayer moving between rows of the citrus, and the spray is being applied on either side on both sides of the sprayer. And you would consider the target to be the immediate trees, canopies that are adjacent to the sprayer. So it's not the next row or the other. It's rather the immediate canopies that are directly adjacent to the sprayer. So this is important because by recognizing what the target is, we are able to adjust the sprayer so that we can have the spray targeted to the target and not beyond. Here is another perspective. This is looking at the sprayer from behind, and we can see in this particular situation we have a full set of nozzles applying spray to the target, which is the immediate canopy. And in air blast sprayer, air blast spray application, the sprayer produces air that is used to aid in transporting the droplets to the target, and the air also serves to provide penetration into the canopy. So this is very critical for canopies such as mature citrus, where the foliage density can be high. We need the air to carry the spray to the target so that the spray can be captured within the canopy. But we do not need the air to carry the spray beyond the canopy. And I will be speaking to some of the situations where that can happen. And it is important to understand that because the air plays a major role in what the outcome of the application. So, at the end of an application, what we are actually interested in is that the droplets, that is the product you're applying, gets to the target. And that can look like this. That is the spray depositing on the target, that is leaves or twigs or other components of the canopy. That could even mean fruits if there are fruits on the target. And this is where these are places that the pests could be residing. And we need the product to get to where the target pest is residing, so that it would perform the pest control activity. It is not sufficient to just apply to that area without getting the spray to the target where pest control would have to take place. And so the on-target deposition could also look like this, and we can see, I hope you can see clearly that this is really a dense canopy. And we want the spray to be applied not just on the periphery like this, but we want the spray to also be able to penetrate and get into the canopy. So taking that into consideration and looking at the fact that the air is a critical part of this application, I want us to take a look at this scenario. We have an air blast sprayer that is on the lower right, and this is also being obscured by an air tank right in front of that, so you can't see the whole extent. But there is an air blast sprayer, and this is in stationary mode, and that is in stationary and applying spray at full blast. So you can see it's going about 50 to 60 feet. What you can see, that is the spray cloud that you can see. And you can also see how high this is going. So we can appreciate the amount of air that could be involved in applying the spray. And the actual amount of air and spray that is applied to the canopy depends on how fast the sprayer is traveling. That is the forward travel speed. So that is the component that meters out the amount of spray that is applied to the target. So it is important to factor that into decision making. And this is a depiction of the air velocity as it exits from the sprayer. So initially, when it exits from the sprayer, there is a sharp drop in the velocity, and then it continues to drop down gradually as the distance increases. And this is important to note because you can attempt to apply spray to the second row, to the next row, but you should bear in mind that the amount of spray that will reach that row would be reduced because of dispersion that is taking place, and also because generally the amount of spray reaching that extent is reduced. That is considering the sprayer moving forward and applying the spray to the target. So in as much as we want the spray to get to the target, we are faced with this outcome or scenarios of outcome where we have the deposition on the target being one of the outcomes. We also have spray ground deposition, that is a spray being applied directly to the ground, or we can also have runoff from the leaves, and then we have drift. And for ground deposition, it's being applied to the treatment area. So to some extent, maybe that is not too much of a concern. It becomes a concern when you're thinking about water runoff during rain and so forth. But when we come to drift, we actually experiencing the pesticide moving away from the treatment area, maybe to a neighboring community, or maybe to the next field. And that is something that is of concern, because now we are having a spray moving out of where we actually intend it to be. So you see three different scenarios being depicted here. The first one on the top is showing a situation where you have sort of a maximum canopy deposition. You have more canopy deposition, that's the on-target canopy deposition. You have some drift loss, you have some ground loss. When it comes to the one down, that's the lower left, you see that in this case, the canopy deposition component is reduced, and there is increase in ground loss and in drift. And then you go to the other scenario, and you see that there is a much reduction in the canopy deposition. And this can represent, different situations. And in the field, we are faced with all sorts of challenges, situations that could result in one or the other of these scenarios. And so it is important to understand the different components or the influential factors that contribute to either having more deposition on target or losing the spray to the ground or to drift. Here is a depiction of different scenarios in the field. You can see, starting off, we have mature trees that are touching. This potentially can minimize drift. If you have a hedge row situation, that would also catch the spray. But if you have a situation with disjointed canopies, with gaps in between the canopies, these provide an opportunity for drifts to occur. So it is important to pay attention to that and factor that in the planning of the application. Ideally, if we have a smart sprayer technology which shuts off the spray when it's not needed and opens the nozzles to spray when it's needed, we can have sufficient savings, at least for the gaps in between the canopy. But it is understandable that this type of technology is, even though it's been established in several years back and it's still being improved, the adoption rate is still low, and not all growers would necessarily have access to this type of technology. We can also look at it from another perspective. Here we see an ideal situation where you have almost all the nozzles on the sprayer applying open, so they are applying spray to the target. This is depicting mature tree situation, mature canopy situation. But we occasionally are faced with tree canopies that are less than those huge sizes, and we have medium tree canopies which don't need all the spray nozzles to be open. So if you look at this depiction, some of the nozzles at the top are not actually applying spray to the target. This is a situation that can potentially increase drift. So this is a case where drift potential is increased. And then we look further at maybe smaller canopies, and you can see that potential is further increased. So it is important to bear in mind that these situations can contribute greatly to drift. And for that matter, it is important to calibrate the sprayer so that the nozzles are the only nozzles that are actually applying spray to the target are open, and nozzles that are not applying spray to the target are closed. And when we look at all the three scenarios here, we can see how that is depicted. There are technologies available, and there are technologies still being developed to automatically open and close nozzles so that this can be achieved. We can experience savings and also reduce potential losses to the environment by drift or by ground deposition. And here I would also want to draw attention to three components of the application that important components to take note of. We have a sprayer, that is the equipment, being one component that needs to be taken care of. We need a well-maintained sprayer, well-calibrated, well-adjusted to the target canopy, and also well-operated. We need spray that is properly timed, not just in terms of weather, but also in terms of the target pest that is going to be controlled. It should be accurately applied, well directed to the target to provide a great opportunity for the spray to deposit in the target canopy and so forth. And then we also have the operator or the crew who must also be informed about best practices in some of these situations that I'm describing, so that they can put that into consideration in planning the spray application, so that there is a great opportunity to get the spray to the target, not beyond, not over the target, and so forth. So, without much ado, I want to discuss a couple of measurements that we have done in our recent research activities, and I have two experiments or two studies to talk about. One is going to be on deposition, which is looking at the spray getting to the target, and the other will look at drift, that is the spray going beyond the target canopy. So here is one study. Actually, there are two different studies. We did a complete factorial experiment where we had four different factors. Fan speed as a surrogate for sprayer size, fan size, and so forth. And we had travel speed, we had nozzle size, and then we also had nozzle rows, number of rows. And in this particular one, we applied spray by varying each of these factors to obtain 16 treatments in one situation in Mandarin and 12 treatments in the second case in navel orange. And we collected spray samples from three heights in the canopy and also at 4 depths. And here are some of the data from that. I just want to show the difference, and we realize that actually the nature of deposition was similar in each of the cases. The treatments were similar in each of the cases. We can see in the Mandarin case, we can see that at the near side of the canopy, we have great amount of deposition, and then at the farther end, we have less deposition. But this is bearing in mind that in the application, we apply from one end, from one side, and then we come back and apply from the other side, so that taking this as a symmetric situation would have the whole canopy covered. So we can see that actually the difference between these two scenarios was that the navel orange had a much denser canopies than the Mandarin. I don't have the numbers here to show you, but that was the situation that we had, so we can look at the difference in the outcome. This is a two-factor interaction that shows the influence of the interaction between two factors, different factors, and I would love to run through this, but for the sake of time, I can speak to some of these and then skip the others. But basically, what we are looking at here is that on the horizontal axis, we have one factor, and then the two lines represent the second factor, and on the right side, on the right axis, we have the deposition that was measured. We can see that, let's say, as an example, the first one we have, we can see that between the two sprayers, the second one is actually a D240 sprayer. The first one is D39 sprayer. The second one is a bigger sprayer, and so we have more air involved. But we can see that between the two sprayers for these scenarios, using more air did not necessarily improve deposition. I could go into that to discuss all of these, but we realize that the general take home from this particular experiment is that using more air did not necessarily improve deposition. So it means that we have to be able to match the sprayer to the canopy, the target canopy, in a way that we can retain the product within the canopy and not necessarily using more air, getting penetration and overly penetrating the spray, the canopy, such that we lose the material. This is a drift study, and I don't have a lot of time to go through this, but I would say that I have a poster out there that discusses this particular study in detail. And this was a study that was done to collect new spray drift data to aid in developing a mechanistic model in part, and also the other ideas to use the data to develop some best practices that would mitigate spray drift. And in this particular experiment, we use a common protocol where we apply a spray in the third drive lane from the edge of the orchard, and we had four lines with artificial samplers. We had cars, we had artificial foliage, and we had string samplers to capture spray at different distances up to 600 feet away from the edge of the orchard. And without going too much into detail, this shows the setup in citrus. You can see the sprayer spraying, and you can see the open field area is a sampling area where we collected the drift samples, and we had two weather stations to capture weather data and use that to also explain the resulting drift that we're going to measure. So these are some of the results from the experiment. And over here, I present the experiment in citrus compared to other crops. We had almond, which presented a bigger tree scenario compared to the citrus, and then we also had grape, which was smaller. So even though these are different crops, they also represent different size canopies. So we can even look at citrus in general and use that to compare the outcome of the application from different canopy sizes. And a major take home from these results is that we ended up with the larger canopy and more taller canopy, which is almond, was a list that presented. It presented less airborne drift initially, but when you look at the drift deposit all the way to 600 feet and projected beyond, it also presented it resulted in the drift. It resulted in drift decay up to a much further distance compared to citrus, which was the next, and then to grape, which was the next. And bear in mind that grape presented a smaller canopy. Next was citrus, and the other was almond. And there is a lot of information from here that I do not have the time to go through. But I also want to just talk briefly about a decision support tool that we have developed in our program that receives the spray application, air spray application inputs. We have the tree characteristics, we have orchard condition, we have the weather parameters, and also the application parameters. And these are received as input into the system, and then this simulates a model, a citrus spray deposition model to predict the different outcomes, that is canopy deposition, ground deposition, and also potential drift. So this is one of the tools we have developed that we are promoting because it has potential to help with decision making in planning citrus application, and also in actually implementing and evaluating citrus applications and so forth. This shows how it can be assessed and so forth. And for the sake of time, I would just end with a take-home message, and basically what we can gather from this presentation, or looking at the outcomes of spray application, and also that is a desired outcome and the undesired outcome, which are the losses, is that effective spray application is not just a matter of applying the spray to the treatment area, but it's more than that. We actually need the spray to get to the target. So it is important to bear that in mind. And in the end, the spray that is actually on the target is a spray that is at work, and not just what has been applied. So with that, I will bring the presentation to a close, and if there is an opportunity for a question.